Good morning, good afternoon, everybody. It's been a while. So today, it's a great pleasure to have Hector come in to give us a brief discussion of his recent work. Hector, just briefly, Hector came to JPL as a postdoc working on the global ocean simulation back in 2016. He's currently a JPL scientist working on a variety of projects, very important projects, including S-mode, Doppler SCAD, and the development of the future Odyssey mission. He has been very productive in the past 7 years. So today he will give us an update on his recent work, the wind work at the air-sea interface modeling study in anticipation of future space missions. Hector, take away.
Thanks, Jimbo. Good morning, everyone. I'm delightful to be here today, at least virtually. So this work has been done in collaboration with a broad community, either at GPL, Caltech, or also across on other continents like Israel, Udi Strobach from Israel, Lionel Renault from France. So very diverse group, and in this group has been focused on recently on the air-sea coupling across between the surface currents and wind mostly. This is in the yep.
Excuse me, just briefly. Sam, are we recording this?
Yes. Recording is in progress.
Oh, my bad.
Okay, so the title today is Wind Mechanical Forcing of the Ocean, a modeling and study in anticipation of future space missions, and mostly, well, in particular, the results are focused on the context of ocean dynamics or potential future potential satellite mission named Ocean Dynamics and Surface Exchange with the Atmosphere. Odyssea, before was WACAM, the Winds and Currents mission, as I reading here. So back in like 10 years ago, Ernesto Rodriguez initiated this concept, and he started to develop this technology, a technology capable of measuring the surface currents and the wind stress simultaneously. Of course, there is a lot of challenges ahead of us. That's the purpose of the study that we are doing at JPL, just to understand what are the potential challenges and how to address them. So first, we started to analyze and to understand the different spatial and temporal scales of the surface currents and the wind stress and how they interact each other. For instance, here in the top panel is an animation of the surface current from a couple ocean atmosphere simulation, where you can see two classes of motions. One that evolve slowly, like for instance, mesoscale eddies, large-scale currents, some mesoscale features in the western boundary currents, but also you can identify fast evolving motions like internal gravity waves, inertial motions driven by the wind stress. And most of these fast evolving motions are in phase with the wind stress, as you can see here in the bottom panel now. In the bottom panel, I'm showing an animation of the wind stress. So as you can see, the scales and the spatial variability of the atmosphere is very different from the ocean, but in despite of that, they can interact each other through the wind stress, through the heat and momentum exchanges, and so on. But today's topic, I will focus on the kinetic energy exchanges between the atmosphere and the ocean through the wind work. Okay, so let's analyze. So the wind work first. Allow me to describe the formalins I will use. So here's the definition of the wind work. So I'm using the Reynolds decomposition just to separate the time in and the time dependent component. So just to, you may already know this definition, but when the windward is positive, it means that the injection of the kinetic energy is from the atmosphere to the ocean, and when the windward is negative, it's in the other way around. The kinetic energy is injected into to the atmosphere from the ocean. Now, looking or start digging deeper in this study, one can separate a high frequency and low frequency motion. As you can see in the animations, it's very easily to identify that there is two kinds of variability, one that evolves fast and one that evolves slow, very slowly. So this is what I did. So I will focus on the time-dependent component, and I split it in two, in a high frequency and a low frequency component. So the high frequency is just briefly is I define it between 1 hour and 5 days. This is mostly this high frequency wind will mostly drive inertial motions, or sometimes it can trigger some internal gravity waves. And on the other hand, the low frequency component, I'll define it between 5 days and 3 months. So this allows me to analyze the seasonal variability of this low frequency component. And this is important to study the low frequency component, because this is mostly the motions that modulate the horizontal and vertical fluxes of heat, momentum, and traces in the ocean. So this is the main reason that I will focus today on the low frequency component. The high frequency component for another talk. So for just by looking at the low frequency, also one can split it in two. One component that is associated to scales larger than a critical length scale. I will define it later, what I meant about critical length scale, and another component whose motions are smaller than this critical length scale. So this allows me to define large scale and mesoscale component. So I will explain it later how I did it. Now, recent efforts have been done in this component, this low frequency component, mostly using satellite data, because, well, now they have this longer time series that they can take into account the internal variability or some long-term trends. For instance, here, one of the most recent papers by Rai et al., they focus on the eddy killing effect. So what they did is they took the geostrophic ocean surface velocity from Aviso, and also the wind stress from Queenscan, and they split it. They split it the data set in two components, one associated to large scales and one associated to the mesoscale component. And they focus on this mesoscale component, which are known that the eddy killing effect can be characterized in this component. So they identified the most negative windward in the western boundary currents, but also that is interesting in this paper is the time series they show. Here again they split this windward in two, and one they call it large scale, and one associated to the mesoscale component, where the eddy killing effect is located. And so what they found is that the eddy source, which is associated to the large scale component, the eddy source is the same order of magnitude of the eddy killing effect. So this is something that puzzled me, and so we're trying to understand if there is some caveats in this, and if there can be if there could be some improvement in the context of Odyssea. So this is one of the main reasons that please keep in mind this. The eddy source and the eddy killing component are of the same order of magnitude. So some caveats, and these caveats are in their paper. So one, they only use the geostrophic velocity. Two, there is a lack of simultaneous measurements of surface currents and wind stress. So this led to an underestimation of the windward, either in the low frequency component, or in the mesoscale component, or in the large scale component. So based on these caveats, the present study aims to assess what major improvements of windward estimations in the global ocean can be expected from a high-resolution coupled ocean simulation, and then to apply these results for a future odyssea. So my nature run is a coupled ocean atmosphere simulation run by JPL, MIT GCM, and NASA Ames, and also NASA Goddard Space Center. So briefly, one of the main characteristics of this coupled simulation is that the ocean component has a grid spacing resolution of 4 kilometers, 90 vertical levels. It also includes tidal forcing, and we have hourly outputs. And on the other hand, the atmosphere component has a grid spacing resolution of 6 kilometers, 72 vertical levels, and also hourly outputs. So this would be my nature run. So to identify and quantify the windward component in the low frequency at mesoscale and large scale components, and eventually to use this simulation for some OSIS studies. Okay, so this is my methodology. So I graph the model outputs. And also, just for comparison, I will compare the coupled ocean simulation against the ocean-only simulation. So there is no, so a forced ocean simulations. I removed the time mean over 3 months from the surface currents and wind stress to define the anomalies. So I will work on the time-dependent component of the windward. And then after that, I apply a low pass filter with a cutoff period of 3 days. And then once I define my low frequency, I apply a spatial filter with a cutoff wavelength of LC, which is my critical length scale that needs to define in an optimal way that better define the mesoscale component. And finally, I compute the low frequency windward associated to meso and large scale components. So first, this is my low frequency component, as you can identify. In the top panel is the ocean currents, the middle panel is the wind stress, and at the bottom is the windward associated to the low frequency component. And as you can see, in the low frequency is still dominated by the positive larger scale component. So it's not sufficient to just apply a low frequency to identify the eddy killing effect. So that's why my next step is to apply a spatial filter and separate what call it large scale from the mesoscale component. So, but to do so, first I need to define a critical length scale that better define the mesoscale component. So what Rai et al. Did, they compute the global windward as a function of a critical length scale. So basically, they compute the windward at different spatial resolutions, ranging from 0 up to 1,000 kilometers. And what they found is that the critical length scale that better define the mesoscale component is about 267 kilometers. So they use this critical length scale to separate large scale from the mesoscale component. So I applied the same methodology to my data. This is in the right panel. The blue line is the one associated to the coupled simulation, and the red line is the one associated to the ocean-only model. So first, what I found is that as a comparison, the ocean-only model computes the same order of magnitude as what Rai et al. Found using satellite data. On the other hand, the one associated to the coupled simulation is about twice smaller than the ocean-only model, which is understandable because in this coupled simulation you have the thermal feedback that tends to reinforce the local winds. So this is one of the first results. Second, so identify my critical length scale of about 270 kilometers. So I will use this critical length scale now to separate my mesoscale component from my large scale component, which is in the next slide. So here's my spatial decomposition of my low frequency windward. So starting from this map, I just split it in two using this critical length scale. So the top panel is the eddy source, which is the injection of kinetic energy from the atmosphere into the ocean. And on the other hand, there is this eddy killing effect where associated to the mesoscale component. Now, as you can see, it is mostly negative, which means that there is the injection of kinetic energy from the ocean back to the atmosphere. Now, something that you have to notice is that the order of magnitude between these two components, there is about 10 times larger the eddy source compared with the Ehrlichen, which is not the same result as what Rai et al. Found. So this is one of the discrepancies. And so we want to understand better what these discrepancies are in this couple simulation that potentially will have will lead us to say that maybe a potential, maybe a simultaneous satellite that is capable of measuring the currents and the wind simultaneously will lead us to a better estimate of the windward. So that's the main idea of this study. So just to really highlight and emphasize the differences between the eddy killing and the eddy source computed from this coupled simulation from what Rai et al. Found. So here you can see this latitudinal profile of the zonal integrated windward. So you can see this, the 10 times larger of the eddy source compared with the eddy killing effect. So this is one of the main results behind this study. And so the idea is, okay, we know that the Rai et al. Have these caveats about the lack of simultaneous measurement. So maybe what they are missing is, so one of the discrepancies between these results compared with Rai is the lack of simultaneous measurements of winds and currents. So this is one of the main message, which lead us to say, okay, will a winds and current satellite mission improve estimation of the windward in the global ocean? So this is something that we are that we address in these past months. And so to answer this question, so what GPL Alex Weintier and Ernesto Rodriguez built a Odyssea simulator that takes into account the geometries, the error field, and the velocity performance, like the error field, and also the wind performance, considering the wind speed error and wind direction error. So they built this simulator. So I took the couple simulation plus this Odyssea simulator to perform an observing system simulation experiment and see if there is some improvements in the windward estimation using this future satellite measurement. So here is an example of 1 day of Odyssea simulated data. So you can see more than 90% of the ocean is covered in 1 day. So I took this simulation and I computed the windward in two seasons. One in January, February, March, and the other one in July, August, September. So I have several data sets here just for a comparison. So the first data set is the Odyssea without the error field, which is the blue line. The second data set is Odyssea, but now taking into account the error field, is in the orange line. And the nature run, which is my couple simulation in green. So this is the first result. The Odyssea is capable of reproduce the windward estimations when comparing with the couple ocean simulation. So there is a great consistency between Odyssea and my nature run. Now, let's see. Now, what I did is I tried to mimic the present satellite measurements, the same satellite measurements that Rai et al. Use. So, for instance, I apply a spatial smoothing to the surface currents and to the wind stress. So, for instance, for the surface current, I apply a smoothing of about 102 kilometers, and for the wind stress, and also I average in time my currents for about 1 week. And for the wind stress, I smoothed it using a 50 kilometers scale. and I use the 12-hour sampling just to try to mimic the QuickSCAT and Aviso observations. But also I use a more sophisticated, well, more frequent observations in time. So for instance, here, this is in purple, I applied the same smoothing for the surface currents, but now I'm using 1 day average fields, and I keep the same wind stress just to try to mimic what Oscar or globe current can give us. So this is the results here. So using Aviso and QuickSCAT, you can get this red line here, which underestimates the windward in both seasons. Now, if you improve the sampling over 1 day, now you have the purple line. So it's a more accurate, but it's not sufficient to match the nature run. Whereas the Wacom sampling, which have the wind stress and the current and the ocean current simultaneously, the estimation of the windward is better. So this is the final message. So the final message is that Odyssea will provide an appropriate set of observations that eventually could give us a better estimation of the windward, but not only the windward, but also to have a better estimation of the air-sea coupling in another way. So this is one of this is the final message and the main message that I would like that I wanted to convey today. So that's all for today. So if you have if you want to dig more about these results, so please visit our manuscript that is in preprint at the Geoscientific Model Development. So in there we describe the seasonality. Well, eventually will be the seasonality. At this moment, I only keep keeping the winter time because at the moment I published this paper, we had just 4 months of simulation. But now we include the 14 months, and now in few weeks, there will be a new version of this manuscript. And now when we include the seasonal variability, with the low frequency component associated to mesoscale, and also the large scale component, and another more stuff that could be of interest for you. So that's all for today. If you have some questions, please send me an email. I will be happy to reply back to you. So thank you. That's all for my end.
Thank you very much, Hector. And we have 5 minutes for questions from the audience. Please feel free.
Yeah, I was wondering what the physical meaning of that critical length scale that you were talking about is. Can you detail a little bit more there? Sorry, I missed what's on the y-axis.
On the y-axis is the spatial filtering, or a cutoff wavelength that you apply to a low pass filter. So what Rai et al. Did is, so they use a top hat. No, it's a top hat function, and they kind of they choose different spatial scales and to apply this filter, this spatial filter. So they apply they use one. So for instance, they use 200 kilometers as a cutoff wavelength, and they apply this spatial filter, and they say, okay, those scales larger than 200 kilometers are associated to my large scale, and those scales smaller than these 200 kilometers are my mesoscale eddies, and they compute the windward. Now, those scales smaller than 200 kilometers are those motions that tends to inject kinetic energy back to the atmosphere. Now, if you change the spatial resolution, the windward estimation will change. And so what they wanted to find is what is the optimal scale that better define the mesoscale variability. But now we know that the mesoscale variability tends to inject kinetic energy back to the atmosphere. So that's what they want. They want to identify the best or the optimal scale, the length scale that better define the mesoscale contribution. So that's what they want. And once they found the minimum windward, they say, okay, this scale is the one that better define my mesoscale contribution. Now, and what they find is after these 270 kilometers, the windward starts going up, which means that you are entering another regime, in the regime where the oceanic motions, well, in the regime where the atmosphere tends to inject kinetic energy into the ocean. So that's what this means. So this means that those scales in the left side of these critical length scales tend to inject kinetic energy back to the atmosphere. And those scales at the right side of these critical length scales, these motions tends to gain kinetic energy from the atmosphere. That is the physical meaning of this scanning that they did. I don't know if it was
So,
clear enough.
Hector, I think also another aspect of the question, if I can interpret, is the vertical axis is the wind work.
Yes, it's the windward.
Walk.
Yes.
If there's a downtrend, that means the air-sea coupling in terms of momentum, the effect is damping the eddies, ocean eddies.
Right. Yeah. Oh, sorry. Yeah, I forgot to mention. Yeah, the y-axis is the windward, but mostly associated to the mesoscale contribution, the mesoscale component. That tends to damp the mesoscale eddies.
That's the term of eddy killing. So
Eddy killing.
killed mesoscale eddies in the ocean.
Jimbo, it looks like Sergey has his hand up.
Oh, I didn't. Yeah, Sergey.
Thank you, Hector, for your presentation. So, one of the discussion topics on our panel is how to handle big data. And, 10 petabytes of data is a lot of data. So what did your workflow look like to actually, process this 10 petabytes of data?
Yes. Yes, 10 petabytes.
On a technical scale, did you just write up some Python codes, or like did you have to stage it from tape?
Oh yeah, well, I use Python. I use task array, task and X array as well, and also I use this MPI 4Pi tools. So basically, I create a tool that can handle these. Well, we distribute the petabytes in several nodes. So, well, hopefully NASA has a nice supercomputer. So I was able to run this war using, I remember, like 100 CPUs. So basically, I use DAS array, DAS, X array, and MPI 4Pi to distribute these petabytes in 100 CPUs.
So far, Hector, we're only use the two-dimensional field, right?
And also, yes, and also that's the other one. Yeah, I use the two-dimensional 2D fields at the surface. But even though now we have 40 months and 40 months on the ocean-only model, ocean-only simulation, so that is a huge data set.
Thank you.
So I don't see any other hands up. Oh, Dimitri.
Hi, Hector. Thank you for the presentation. Very interesting. Could you go back to the slide where you showed decomposition? I didn't have enough time to really digest this, and there is one question which really bothers me. Yeah. Thank you. So you define this as a wind work, right? But I'm looking at the units, and I'm not getting the work units if I do this scale multiplication, right? Wind stress times ocean velocity, right? So we have units Newton per meter squared times meters per second, and I'm not getting units of work, which is joules, Newton by meters.
So this
Well,
tau stress,
yes, so stress is Newton per meter squared,
Mm-hmm.
and you multiply by velocity, which is meters per second. How do you get units of work?
So it's Newton meters per square times.
I'm sure I'm missing something, but I can't figure out.
Yeah, I need to do the question. I need to write down the units, but I'm sure. Yeah, I did. I'm sure that we have the right units. So Newton is kilograms meters
So what I
second.
suggest is, Hector, you follow up with Dimitri offline.
Yeah.
Because we are running a little bit over time. So in order to leave time for the panel to discuss the Cliver pause.
Yeah.
So we can actually close this seminar. Again, thank you very much, Hector, for
Thanks
talking
to
to
you,
us
Jimmy.
and present your work.
Yeah, thanks. I hope it would be clear enough.
Yeah, this is
so much,
great,
Hector.
great presentation. Thank you.
Yeah,
Thank you.
so for everybody who is part of the POS panel, please stay on. And for those that were joining in, if you could sign off at this time. Thank you. Thank you so much,
Thank you.
Hector.
Thank you. Bye.